Okay, physical science time is right, Sage. That's exactly what we're up to today, physical science time. And today we are talking about nuclear radiation, its causes, effects, uses, detection, and finally, and most satisfyingly, math. That'll be great. I don't know if this is a problem with me or with you, but I'm going to say it's with you because it'll help me. No, this is beautiful. Nuclear radiation, we're talking about its causes, effects, uses, detection, and math. The objective, as I was reminded to write down so gently, is observe and diagram nuclear radiation. Observe and diagram. Observe and diagram nuclear radiation. Let's start from there. Let's start from radiation. What you can tell that nuclear in this context is being used as an adjective to describe radiation. What is radiation in general? Yeah. The most general. Related to a word you also know from math, from the Latin. That is not what I was looking for. I see what you're getting at. What is the math word I'm looking for, do you think? That has to do, that sounds like, I'll say it that way, radius. There we go. We're thinking about, I'm going to put a little approximate on here. It's like the radius of a circle. Remember, a lot of times when some people tell us that we're supposed to think of math as the most basic kind of learning. It is definitely the simplest, maybe not the most basic, but we can have arguments about that at a different time. But the radius of a circle is that idea that it is doing what? The radius of a circle is the what? What? Say it to me. You tell me. Okay, that's not wrong. Yeah, it's from the center to the outside of a circle. From the center outside. Would it still, it's a line segment, so could we still say it's from the outside to the center? Sure, but the way I've always been explained it to me, and the way that will serve our uses here best, is that it's a line segment, which I know you're not supposed to have an arrow on a line segment. Array has an arrow. Don't at me. But I'm putting that arrow there to indicate that we are thinking about it as moving, even though it's a static object, from the center outward. And this is the radius of a circle, r. So nuclear radiation, and the reason I was specific about that it's from the center out, radiation is, let's also relate it to this thing. No, I'm trying to draw a good thing. It's not grass. No, it has a pipe, and it has this thing, and you turn this little nut. Radiator, a radiator. If it wasn't such a pain to turn the camera back to the way it's supposed to be, I would show all of the YouTube viewers, all 3 of the YouTube viewers, I would show that there's a radiator over there. And what does it do? Both of these things, this radius and this radiator, have to do with the idea of what? A central thing, things coming out from a central place. In the case of the radiator, heat or warm air coming out. I guess warm air doesn't really come out. Heat itself comes off of the radiator. In the case of a circle, it is that line which which emanates or broadcasts from the center of the circle outward. Yes. That's a really neat place. Let's do related to radiator springs. I mean, everything. It is one of my fundamental philosophies that if a word has the same root word, we should be able to relate it in some way. So let's think about radiator springs. Why would it be called that? If Disney copyright strikes this video and I have to make another one, I'm going to be frustrated with you. A radiator on like an old car. Look here, I'm going to draw like an old car. This is going to be really good, actually. I can already tell. And this is the little guy. Oh, wait, people don't drive cars in the Cars movies, right? They just have eyeballs, and this one is going to have this creepy kind of eyeball. Why is his eyeballs in two different? Why is one eyeball? Crap. Don't say crap. I'm going to have to cut this video. I've bamboozled myself in my own bad drawing, which actually the drawing is not that bad. I'm just an idiot. There we go. There, he's got little lips. These are wheels. Which in the Cars universe, they like lift them up. Other brands are available. I don't know how to prevent myself from getting added by Disney for drawing something from the Cars universe. I don't think they'll mind this style that much. But in the Cars universe, they can use them as like little grippers too. They can like wave at each other with their wheels. Anyway, so Radiator Springs is named that because it sounds old-timey, and because of this part, which I drew first of this car. What does it do?
The radiator.
It's the radiator. What does the radiator do in a car? Do you know? Yeah, okay, so we think of it as what cools the engine down, because what's happening is the engine gets really, really hot when it operates because of friction and various other things. But it gets really hot, and in order to cool down, that heat is radiated outward. Remember, the loss of heat, this is from chapter 5 we talked about, the loss of heat makes things cool down, right? That's heat and cold are kind of opposite sides of one coin. And so this moving of heat outward is the job of, again, a radiator. The radius is that idea of a line segment emanating from the middle of a circle outward, and a radiator is an object that emits heat outward from a central, not in this case point, but a central object. So radiation, in general, is the emission of matter or energy, I'll put it that way, matter or energy outward from a central, I'll put point, I'm going to put in quotes though, because, you know, mathematically, we've been talking about math a little bit, we will talk about math more. A point is a arealess, dimensionless dot. We do oftentimes think of radiation as having a point source, but in reality, that point is not dimensionless in reality. So the emission of matter or energy outward from a central point is called radiation in general. Now, the sun, as Miranda says, does emit radiation. I'm going to draw the sun now. Look, it is radiating. The energy that the sun produces radiates out from a central point. This, I'm going to draw the sun in splendor here. Ooh, it's a girl sun now. That's kind of sexist. Don't tell me I said that. So this is the sun, and you can see I'm drawing some beautiful radiations outward. And here's, oh look, I was going to draw this, but I'll just put it right here. Look, it's radiating outward, and some of that energy gets onto the earth. Nice, right? So that's where we get a lot of like the fact that the sun is shining today is because the sun is radiating energy outward from a central point. So that's a kind of radiation. This is a kind of radiation. This and this are a kind of radiation. Today we are talking specifically and finally about nuclear radiation. So that energy or matter that radiates outward from a nucleus. That's the point of today's discussion. So that energy or matter, remind yourself that these are the two observable things about the universe. We get into a little bit of, could there be more, right? Is love real? Is there a God? Things like that are outside of the observable universe, and so we don't consider them scientific. Not that they're necessarily false, but that they are not scientific. But these are the two observable categories of stuff in the universe. So that energy and matter which radiates, I'm not going to put that in quotes, I'm going to underline it, radiates outward from what then? If we're talking about now nuclear radiation specifically, which radiates outward from the what? No, I knew you were going to say that. No, from the what? If it's nuclear radiation, remember nuclear is the adjective, the nucleus, from the nucleus of, I'm going to be specific because someone already said the word cell, of what? Of a cell?
Yeah.
No. Of what? Come on. We just talked about this. An atom. An atomic nucleus. An atomic nucleus. What is the atomic nucleus made out of? Remind yourself from the last chapter. We'll try one more time and this time get it right. Protons and neutrons only. Protons and neutrons. Where are the electrons?
Outside.
Yeah, they exist outside of the nucleus. They exist in, either we think of it as an electron cloud or electron orbitals, whichever way we're deciding to think about it. They exist outside of the nucleus in either case. And so we have protons. I'm going to draw those as purple. I'm going to draw the neutrons as, okay, you know what, I've already made a mistake. I told you purple and I did yellow. The protons in this diagram are orange. I said yellow, but I meant orange, so now I've got a triple mess up going on here. The protons, which have a positive charge and a mass of 1, I have drawn as orange. Yes, okay, we're all good on that. The neutrons, which have a neutral charge, a 0 charge, and a mass of 1, I have drawn in purple. This is the nucleus of an atom. If we were to draw the electrons, which I guess I'll just do, remember they kind of just exist out here, floating around, more or less at random, nearer or farther from the nucleus, depending on where the wave manifestation takes them, I guess. But this is what we're going to focus on, the nucleus. What's holding it together? You remember? What force? Remember, forces are what cause accelerations in objects. You remember from the beginning of the year. What forces are acting on these particles? Not gravity. Why not gravity? Well, they do have mass. So is gravity technically acting on them? Yes. But why would gravity not have a very strong effect on them? They have the tiniest little mass. They are the tiniest massive particles that we observe, other than quarks. Remember, by the way, that each of these neutrons and protons is made up of quarks. The protons are made up of 2 ups and 1 down quark, and the neutrons are made of 2 downs and 1 up quark. But what forces are acting on these? The strong nuclear force is acting on them. The strong nuclear force is a force that holds together any 2 nuclear particles. The strong nuclear. It holds them together like glue. In fact, because it's kind of like glue, we call the particle that intermediates the strong nuclear force a gluon. You don't necessarily need to know that. What other forces acting on these, though? Let's think specifically about these positively charged protons. They have a strong force holding them together. Is there anything pushing them apart?
Yeah.
Think about that they both have a positive charge. What would be pushing them apart? Yes, the electromagnetic force is pushing these 2. I'm actually going to write it out. I was going to write EM, but I'm going to write this down. Electromagnetic force is pushing those 2 protons apart. Now, I hope you're starting to see one of the reasons why neutrons are important in a nucleus. And in fact, we might even be able to say the reason neutrons exist is because do they interact with a strong force? Yeah, they do. You can see that all the nuclear particles interact with the strong force. They stick together because of the strong force. But do the neutrons interact with the electromagnetic force? No, because they're neutral. You see? Are you with me so far? Neutrons are neutral, and they're nuclear particles. So they do interact with the strong force. They do glue other nuclear particles together. They provide that glue, okay? But they don't have the push apart of the electromagnetic force. So they provide gluing together of the nucleus without providing push apart of the nucleus. Are you kind of with me so far? We could say the role or the purpose, those are both kind of, I'm hesitant to use those terms because they don't think about this, right? But the benefit of neutrons being in a nucleus is that they help hold it together because of the strong nuclear force. This is fine. Right now, in this nucleus that I've diagrammed here, these forces are probably balanced. It's neither collapsing in on itself because of an overabundance of strong nuclear force, nor is it being pushed apart by the electromagnetic force. Those 2 things are trying to happen, but they're counterbalanced. The forces are balanced, yes? Now, what happens if we get a much, much, much bigger nucleus? I'm not going to draw it that much bigger because I don't want to take up all my board space, but let's say we got some protons and neutrons together in here. Let's say we've got a big nucleus like many of these atoms down here on the periodic table, or many of these atoms down here on the periodic table. Do you notice a relationship between all of these and all of these? They're all what? They're big, for one thing, right? How do I know they're big? Well, they have great big masses, and they have larger atomic numbers, right? So they have more protons and neutrons. Remember how we learned about this last time, yes? They're bigger, and they're always radioactive. Because what happens in these, I'm saying a lot of stuff, but I'm not really writing anything down, so I hope somehow you're writing this down. In bigger atoms, the electromagnetic force, I'm going to write in green, electromagnetic force, I'm going to specify electromagnetic repulsion overcomes the strong force. I switched fonts halfway through because I remembered you guys can't read cursive. So if the strong force is stronger than electromagnetism, The strong force is stronger than electromagnetism, but it acts over smaller ranges. Do you remember this from our 4 fundamental forces of the universe, SUG? Do you remember SUG? That the strong force is the strongest, decreasing strength. But the strong force also decreasing range. It acts over the smallest distances, which is another one of the reasons why gravity doesn't really come into play here at all. Technically it does, but we don't have to worry about it because it's so small at that scale. So the strong force is the strongest of the 4 fundamental forces of the universe, but it also acts over the smallest ranges. And so by the time even we get to the size of this atom, the strong force is completely tapered off. I shouldn't say completely, but it has mostly tapered off over the size of this atom. And so the strong force is gluing them together, but the electromagnetic force acts over greater ranges, and so it's more effectively falling apart. And that falling apart of an atom is nuclear radiation. And that's why all of these larger atoms, all of these larger elements are always radioactive. This symbol, this little symbol here is the symbol, the international symbol for nuclear radiation. And on this chart, it indicates that all of the isotopes of that element are radioactive. Almost all of the elements have some isotopes that are radioactive, not iron, but almost all of them have some radioactive isotopes. But these ones that have this symbol only have radioactive isotopes, only have isotopes that fall apart. The relationship I commonly draw for this is that if you're building with Legos, you could build like a little, other brands are available, but you could build little like 2x2 bricks into a cube and it would be really sturdy. You could probably like throw it at the floor and it would stay together. But if you build great big 1,000-piece castle and drop it, it falls apart because it's bigger. Things that are bigger are a lot of times more inherently unstable. That's not a rule of the universe. It's just a way that we can kind of understand this. The bigger atoms tend to fall apart more, and that falling apart is nuclear radiation. So what is the effect of that? How do they fall apart? When this falls apart, there's a couple different ways it can happen. For one thing, like our castle, it can just undergo what we call spontaneous fission. Spontaneous. In fact, for larger atoms, spontaneous fission is the main way in which they decay. They just fall apart. They might break in half, they might break into 1/3 and 2/3, but they basically just fall apart. Another thing they can do, like in this group's lab, is that they can emit smaller bits of radiation, such as an alpha, beta, or gamma particle. And that causes it releases these particles, and it becomes a little bit more stable. When it releases that particle, it's a little bit more stable. And then maybe it's still unstable, and so it releases another particle, and that becomes a little bit more stable. Kind of like in my analogy, if you have your castle and you kind of gently take off bricks, and it's a little bit more stable each time. So the effect of this unstable nucleus is that it emits these particles. They radiate outward from the nucleus of an atom. It's nuclear radiation. How is that useful to us? You know about nuclear radiation. In what context have you heard about radiation before? Okay, bombs. Personally, because of my own philosophy, I would hesitate to say that nuclear bombs are useful in the strictest sense of the word useful, but I know what you're getting at. Yeah, okay, but they are used in bombs. You're correct about that, Lucas. They are used in medicine. That's, I would say, their primary use is that these particles and the way they interact with your own tissues can be measured, and they can be used to show things like in a PET scan. PET stands for positron emission tomography. It's a way of looking inside of a human being using nuclear radiation. One key thing about this, though, is that this is undetectable to human beings. This can be happening all around us right now. We would have no idea. We would eventually find out, because if it was happening strong enough, we would start throwing up and lose all our hair and then die, because that's the effects of nuclear radiation on a living organism. But we can't detect that naturally with our own senses. We can't see or hear or taste or smell. So we need some kind of detector. And I'm going to erase the stuff over here real quick, and then we're going to talk about the way in which it's detected. There are some tools that we use to detect nuclear radiation. Can you guess what they are? A Geiger counter. Let's bring that boy out. And like I said, I'm not gonna bring the uranium that I have in here because I don't want to have to bring all the goggles and everything. I don't want it to get in my coffee. But this is a Geiger counter. This is a Geiger counter. This is a headphone. So you know how headphones work. This is a Geiger counter. And what the Geiger counter does is it has a pair of, in this wand, there's a pair, in this case there's a tube, but they can be a pair of discs. But there's a tube inside of a tube. And since these particles, not gamma, but since these two particles, as we'll learn about in a second, have a charge, when a charge gets in between the internal rod and the external rod, or in the case of the discs, if it gets in between the discs, it makes a circuit. Remember, we talked about electricity. And so if a charged particle gets in between these two things, the circuit is completed momentarily, and it'll make a clicking noise that I can hear with my headphone. I'll tell you when one happens there. One just happened. And I have this set to 100 events. So every time 100 charged particles get in here, this makes one click. I just switch it to 1, so it should happen 100 times more often. Listen. So can you hear it if we're quiet? The little clicking, one of the other ones has it on something like a loudspeaker instead of a headphone. But every click, the way I have this set now, every click means that one charged particle has interacted with the Geiger counter. I can set it to times 10, which means it'll click for every 10 times, or times 100, which means that every 100 particles, it'll make one click. A Geiger counter is used to detect these things because, once again, we cannot detect them with our senses. And so we detect them with, in one way, a Geiger counter. We'll do that in the lab in a little while, hopefully, if there's time. Another way we can do it is with this electroscope. Electroscope. You might remember this from when we did static electricity too, because it works on the same principle. I mean, it's the exact same thing as what we did. But basically, if a charge touches this conductive rod, these two leaves down here will separate. If a charge touches this, whether it's a positive or a negative charge, both of the leaves will take on that charge, and because they have the same charge, they will separate out from each other. So in the presence of these charged particles, which can be positive in the case of alpha decay, or positive or negative in beta decay, in the presence of those charged particles, these leaves will separate. Right now, they're like moving around because of inertia, and I'm moving the vessel that they're in. But if we have this sitting still on a flat surface, and they spread out, that indicates the presence of charged particles. Or once again, we can touch it with something that's charged, and that will cause them to separate as well. That's an electroscope. And the other thing we use to detect the path of these charges as they flow out of the nucleus is either a bubble chamber or a cloud chamber. And these both work on the principle that these particles are really energetic. And so as they travel through some medium, in a bubble chamber, it's superheated liquid, and in a cloud chamber, it's vapor. As they travel with their energetic little bodies through this medium, they will, in the case of the bubble chamber, cause boiling, and that will cause little gases, bubbles, to form along their path. And in a cloud chamber, they will cause condensation. They will cause liquid to form along their path. Let me show you a little picture of those, because they kind of have cool little patterns that they... This is a picture of, this one here is a bubble chamber, I believe. This is a picture of the readout of a bubble chamber. So each of those lines indicates the motion of one of these charged particles. If I remember right, I think the beta particles leave a straight trail, and the alpha particles leave that kind of curly little trail. So kind of a neat figure. Okay, so they can be detected in this way, right? We know they have some uses in medicine. The effects of the breaking down of nucleus are nuclear radiation, and the causes of nuclear radiation are instability in the atom. So let's do the math. This is the fun part. This is the thing that everyone showed up for today. there are 6 kinds of nuclear radiation. We're going to have to do this really fast. I'm going to build this little table. Let me assure you, freshmen and future freshmen who are viewing this, we will do this worksheet kind of together. We'll start out on this. So you'll get more experience and practice with this in the future. But for now, I'm just going to write down the 6 types of radiation and tell you a general way that we do this, and then we'll talk more about it in detail after the video, or probably tomorrow after the video. So we have 6 kinds of nuclear radiation. I love drawing tables. For each of these, we're going to have a symbol, a name. The name column I made way too small. A mass, a charge, I know I want to put an example, but I'm wondering if there's another thing that I need to put here. Well, let's just have example be here, and then I'm sure I will think of the other thing. Okay, so the first one is this symbol, which looks kind of like a little fish. It's the Greek letter alpha. It's called alpha radiation. Oh, I know what I wanted to put on here. Let me mess everything up for you. Almost all of them have 2 symbols, and so I want to put like alternate symbol as a... Really would have probably been smarter to have the name over there anyway, but I'm going to put alternate symbol here, name, mass, charge. One thing you need to bear in mind as we're doing this is that these things are, how are they interacting with a nucleus? What is the verb that they're doing of the nucleus? Here's the nucleus of an atom. They are what? All of these things as they are, they're what? They're leaving, they're radiating. Yeah, they're mathematically, they are subtracting themselves from the nucleus. Remember that, okay? So when we're working with these things mathematically, subtraction is kind of the name of the game. So the symbol for this is that little alpha. The alternate symbol is a helium-4 nucleus. So it has 2 protons. I should have made that column bigger. This is the other symbol. It's a helium-4 nucleus. 4 being the mass of the nucleus. It has 2 protons, that's its atomic number, and the fact that it's a +2 charge means that since helium normally has 2 electrons, if it has a +2 charge, now it has 0. It has 0 electrons, so it's just a nucleus. So we call it a helium-4 nucleus. This is called alpha decay or alpha radiation. Its mass, can you guess? I just told you. 4. For what? If we're being specific with our units. Atomic mass units, good. Charge?
0.
Mm-mm.
+2.
+2. Yep, +2. An example I'm aware for this one is uranium-238. Uranium-238, we say this little arrow as undergoes alpha plus what's left. Well, if it was, let me give you an example of this math. If it was 238, its mass was 238, and it has lost this helium-4 nucleus, what is its new mass? 234. Since it's helium, we know that 2 of those were neutrons and 2 were protons. So now instead of being uranium, it's lost 2 protons. So what is it now? It's not uranium-234, it is thorium-234. So this is how we do these kind of problems. We start with some isotope, we're told the decay mode, and then we subtract that decay mode from the mass and the protons of the isotope. We are never going to get through this in 1 minute, but we'll just keep going for a second here. We'll probably have a part 2 where I don't want to leave this up on my board all day, but whatever. This is the boat that I've gotten into. This is what we're going to sail in. Is the mic on? Yes, okay. Physical science time again. Today we are continuing our discussion about how to solve problems in nuclear reactions. So let's just head this nuclear reactions. We are going to rebuild the chart, don't worry. I kind of ran over my diagram. We had talked a little bit about, during the bell work, this was our bell work example, we had talked a little bit about how we set up these problems. And I highlighted the locations wherein we find the information we need to solve the problems. The problem we were given, I'll read it to you from the bell work, said, protactinium-231 undergoes alpha decay. Write and solve this nuclear equation. That's what the bell work said. So from the problem, we know that it's protactinium-231. This protactinium, the symbol for this, right, the word protactinium was in the problem. Where did I get this symbol and the atomic number? The periodic table. I found the mass from the problem. It said 231. It specifically told me protactinium-231. Undergoes is this arrow, and then from my chart that I'm going to continue today, we know that an alpha particle is also a helium-4 nucleus, which I've written there. Could we have written this as an alpha particle like that? Sure, that's fine. This can be more helpful to people who are still learning how to do this. So the actual math we did was these two. 231 minus 4 is 227, and 91 minus 2 is 89. Where did this 231 come from? That's the what of what? The mass number of protactinium-231. Where did this come from? Use the same kind of verbiage. It's the mass number of the helium-4. And since a helium-4 nucleus is leaving the protactinium-231, we subtract them, giving us a new mass number of 227. Since the atomic number of the protactinium was 91, and the atomic number of the helium-4 nucleus was 2, we subtract those because the helium-4 nucleus, again, is leaving the protactinium-231 nucleus, giving us an atomic number of 89, which gives us the element actinium, again, looking at the periodic table. Okay, so let's continue our chart. I think it looked like this. I think it had that leg. It had this. I think it may not have even had one of those over there, but now it does. For each, I'm going to draw 6 lines here. 2, 3, 4, 5, 6. I'm going to have to squat towards the end probably. Over at the beginning we had symbol, I believe. And then we had an alt symbol. And then we had its name. Yeah? And then we have its mass. And then its charge. Let's also put in here, no, okay, let's not then. The other one that I should put in there is its number of protons or its atomic number, because that would tell us that basically this column gives us how to do this math, sorry. And if there was another nice little column, it would give us how to do this math, but you should figure that out on your own, I guess. So we already had alpha particle, the helium-4 nucleus. It's called alpha. Its mass was 4. Its charge is 2+. And in our example, well, let's just use this one. That's an example of it too, isn't it? We had an example yesterday, which is why I wanted you to feel comfortable doing this bell work today, and that you didn't. That's okay. You're not in trouble. You just disappoint me. Okay, the next one we have, I think we started writing beta minus, right? Oh, we started with beta plus. Fine. Another symbol for that is an electron, but with a positive charge, which we call a positron, which is a piece of antimatter. This is called beta plus. This one your book does not talk about at all. So listen to me very carefully. When your book says undergoes beta decay, it doesn't specify beta plus or beta minus, but your book doesn't know about beta plus, and so every time your book is talking about beta, it means beta minus. You should be aware, and on the test there will be beta plus, and on your worksheet there is beta plus. But anytime the book says beta decay, it means beta minus, okay? Mass, no mass. Charge, positive charge. Here's an example of that. I have my iPad brand, Apple brand iPad tablet of science here. Other brands are available. And I'm going to tell you that astatine-210 undergoes beta plus decay. Astatine-210 undergoes beta plus decay. So what's left over? Well, let's think about this. How will the mass of our new thing, let me do some more vocab. We sometimes call this a parent isotope. Okay? Do you know why we might call this a parent isotope? What's it doing in a sense? It's the OG, yeah, but that doesn't necessarily, it's almost like it's birthing an alpha particle and another thing. What do we call this, do you think? I've said this phrase before. This is called the decay mode. Decay mode. Mode means, in French, it means style. It's like a kind of thing. Like if you're in beast mode, that's a way your being is in beast mode. Other modes are available. The decay mode here is the way in which it is decaying. What's the word decay mean? No, not die. It does not mean die. It means after the thing has died, it means it does what? Be very basic. Talk to me like you would to a second grader. It what? Say it again. It falls apart. Decay means fall apart. This is the way in which this unstable atom, this unstable isotope, falls apart. Is in this case an alpha decay. Okay? And then this is called the daughter product. Daughter product. So the parent isotope, this could maybe say daughter isotope too. Either way is fine. The parent isotope undergoes a decay mode, becoming the daughter isotope. If it changes elements, what do we call that? There's a special word for if it changes from one element to another. No. You should know this. This is one of your vocab words. It's also what Hennig Brandt was trying to do with that urine. Remember he had that urine, he was trying to change that into, well, yeah, he was trying to change it into gold. He was trying to change whatever element was in the urine into gold, which is called, and the alchemists called it this, transmutation. So this specifically illustrates a process called transmutation if the element changes. Okay, back to our chart. So if this astatine 210 undergoes beta plus decay, what will the daughter product be is what we're trying to solve for. So we know it's going to be something. How is the mass going to change? How will the daughter product's mass, in this case, relate to the parent isotope mass? It'll stay the same. So we're still going to have a mass of 210. Why? Because it has no mass. Because no mass has left it. A positron is left, but that positron has effectively no mass, and so no mass has left the parent isotope. So it has the same mass. Now let's think about this. It was astatine, which has a number of 85. You don't have to put this number in when you write them, but sometimes it is very helpful. Think about this. If a positive charge is leaving the nucleus, a positive charge leaving, will this number go up or down? Down. So now it's, instead of astatine, which is 85, it'll be 84. So now it's not astatine anymore, it's, no. Astatine is AT, number 85. Nope, polonium. It's now polonium. So that's kind of the method we use to do these. We find its mass, depending on what the decay mode was. We then find its new number, depending on what the decay mode was. And we then tell, given that number, what is the new element. Was this transmutation? Yeah, it changed from astatine to polonium. So it did transmute. It changed what element it was. Can you guess what the next kind will be? Beta minus, which is an electron being emitted from the nucleus. Remind me why in general, why conceptually and in general, do any of these happen? What's getting better is not the right word, but why would this do this? It doesn't decide. What's becoming truer about it? It's becoming more what? When it decays, it becomes more. Remember we talked yesterday about how if you take it becomes more stable, less unstable. Okay, so an electron is leaving this nucleus because basically in these two, do you remember our four fundamental forces of the universe? We already talked yesterday about the strong force and electromagnetism, right? We talked a little bit about gravity. What was the other one? Weak nuclear. In both of these, either a proton changes into a neutron, which releases a positive charge, or a neutron changes into a proton, which releases a negative charge, and the fact that happens is because of the weak nuclear force. Proton changes to neutron, or neutron changes to proton, which actually we use this symbol. If a proton changes to a neutron, it releases a negative charge, and if a neutron changes to a proton, it releases that's not right, negative charge. The first one was positive. There we go. The weak nuclear force governs that interaction. So because of the weak nuclear force of the universe, sometimes an unstable atom will change one of its protons to a neutron, which will release a positron. And sometimes, also due to the weak nuclear force, a neutron will change to a proton in the nucleus, releasing a negative electron. So we call this beta minus. Both of these are governed, again, by the weak nuclear force. What would the mass of that be? It's that of an electron, so it is 0. But what's its charge? negative. Now I have to look up an isotope that actually does this in real life. I want these to be true. In the past, I sometimes have just made these up, but I really would like them to be true if I can. Okay, rhenium-186. Sorry, Re, it's not rhodium, it's rhenium. Rhenium-186 undergoes beta minus decay. Let me show you in this one. We can write this another way, basically, just like we could for the alpha decay. It's not that every time it's beta plus, we write a plus sign, and every time it's beta minus, we write an E with a minus sign. I'm just showing you there's two different ways. Remember, like we said in this one, we could have used the alpha symbol instead of this. I'm just going to show you this one in a different way, okay? What is it going to become? How will its mass change? It won't. So what's the isotope? What's the mass of this new isotope, this daughter isotope? It's 186. Rhenium was number 75 here, it looks like. Yep, 75. And an electron is leaving. A negative charge is leaving. So what will happen to the atomic number? It will go up one. So now it'll be 76, which is osmium, OS. In this case, you see I didn't write my atomic numbers. You don't have to. That's an option. So you have two options with these that you can choose to do. You may or may not write the atomic number, and you may choose to either write the symbol or the alternate symbol for the decay mode. Good? Okay. The next one is gamma. That one does not have an alternate symbol. Gamma has no mass and no charge. Gamma is a kind of light that is emitted. It's a high energy kind of light that is emitted by some elements as they decay. Not every element as it decays emits it, and it's not the only source of gamma radiation, but this is one of the sources of gamma radiation. And it always, at least in my experience from what we found, it always accompanies some other decay mode. It's never just gamma. It's always gamma as a addition, like a little side dish. You guys know about side dishes. Some better than others, I'm sure. I have to find one that actually undergoes gamma decay, which apparently, no matter how many times you look, it's pretty rare. What kind of thing is gamma? It's light. Oh, I didn't know that. Say it again. Hulk into Hulk. Hulk turned into Hulk because of gamma radiation? I would not attempt that because in real life, gamma radiation either kills you or gives you cancer. So I would not recommend trying to turn into the Hulk. Golly, I'm having a rough time finding one that does gamma. Nope. Hey, no, we're not going to talk about that right now, Sage. We're trying to do something. Here we go. Okay, cobalt-60 undergoes beta minus and gamma. Okay, so cobalt-60 undergoes beta minus and gamma. How will the gamma change it? It won't. The gamma doesn't change it at all. It just also happens. How will the beta minus change it, though? Well, will its mass change? No. Still going to be 60. But now, instead of cobalt, it's losing a negative charge. Nickel. Good. So the gamma here did not change the mass or the atomic number. It was the beta minus that changed it. Okay? Nope. sometimes it's a different thing too. It can be alpha or beta plus or beta minus or the next thing that we're going to talk about, which is electron capture. The electron capture symbol is that little epsilon, and it's also symbolized like the other one was as a electron, but you'll see there's a little bit of a difference here. Electron capture. Mass, it's an electron. 0, what's its charge? It's an electron, negative. But this one, instead of subtract, it adds. It's capturing an electron. In this decay mode, the unstable nucleus absorbs an electron from its lowest energy level. So it already has electrons, as almost all atoms do, and it just absorbs one of those electrons into the nucleus. And then that, kind of like the opposite of this little thing here, that electron combines with a proton to become a neutron. So in this case we have, oops, my iPad turned off. I mean, my tablet turned off. Other brands are available. 145, Promethium-145 undergoes electron capture, but check it out. In the electron capture, we put the electron on the same side. It's combining with the nucleus. So, will its mass change? Does the electron have mass? No. I mean, not in a way that's going to change this number. So 145 is still it. But now, it has absorbed a negative charge. So it's going to, instead of being promethium, which is here, it's absorbing a negative charge. So its atomic number will, if it's absorbing a negative charge, it will go down. So now it's neodymium. Was that Nd? So in this case, the decay mode goes on the same side as the parent isotope because that parent isotope is absorbing an electron, not emitting an electron. And the last one that we talk about is spontaneous fission. This is the example where you drop your Lego castle and it just falls apart in some basically random way. Something's going to come out the other side, but it's you don't determine that. Oops, spontaneous fission. Fission is the falling apart. Fission means things fall apart. You know what a fissure is? Have you ever heard of a fissure? A fissure is like a break in the ground or a crack in something. And you can have fissures on your lips, and those are cracks in your lip. A fissure is something that is broken. And so spontaneous fission, because we don't know. It just falls apart in some basically random way. It will be something, right? For instance, if we had, I don't know, if we had arsenic 75, that might be too complicated. I'm going to try to use it. If we had oxygen 18, which is, it does not actually in real life undergo spontaneous fission. But it might, when it falls apart, it might become carbon and helium because those two things add up to the same number of protons as oxygen. You see, that doesn't actually happen because oxygen doesn't undergo spontaneous fission. But these things that do undergo spontaneous fission will fall apart into elements that add up to the original. But you don't need to worry about this one. You won't have math for this one. It's just, it does exist. So these are the kinds that you need to know. These are the 6 kinds you need to know. These top ones are the 5 ones you need to do math with. And this one is kind of like a side dish. So it shouldn't, really there are 4 ways you need to memorize. Also, astute observers of charts will realize that these 2 things have the same effect. Losing a positive charge and gaining a negative charge have the same effect on the nucleus, but they're different decay modes. Does this help a little bit? Do you feel taught? I think yesterday our objective was to observe and diagram nuclear radiation. To me, it seems like we have met that. We set out yesterday to illustrate the causes and effects and uses of nuclear radiation and tell the types, and I think we've done that. This will be the thing that you do this chapter. So I would say if you know your vocab in this, you'll be at least silver and probably gold. Do you have questions?